In this video, we're going to look at ideals. We're going to start, of course, with the basic definition. We're going to let S be a subring of a ring R. And we are going to say that S is a two-sided ideal of R if and only if S has the following two properties. And the first property is that for every element inside the ring R and every element inside the subring S, we have R times S belongs to set S. And the second property is that for all R inside ring R and for every S inside subring S, S times R is also inside S. Now, a couple of little things to make notes of. If R itself is a commutative ring, then we have property 1 if and only if we have property 2. And the other thing is that we usually use the word ideal to mean a two-sided ideal. It turns out that you can talk about one-sided ideals if you have this first property. A lot of people would describe that as S is a right ideal, and if you have this particular property, people would describe this as S is a left ideal. In our particular course, those one-sided ideals are not going to actually play any role. To show something is an ideal, if you already know that it's a subring, all you have to do is verify that both of these properties are true. If you already know that R is a commutative ring, then showing either one of the properties works, because in a commutative ring, RS and SR are the same element. Well, let's actually now look at a couple of examples. So our first example, we're going to show that N times Z is an ideal of Z. Now, N times Z is just the set of NKs such that K belongs to Z. In other words, N times Z is the set of multiples of the integer N. And to show that N times Z is an ideal of Z, what we need to do is we need to let K be any element of Z, and we need to let B be any element of N times Z. And because Z is a commutative ring, we need to show that K times B belongs to the set N times Z. Well, look at this. K times B is equal to K times N times L, since B inside N times Z implies B is equal to N times L for some L inside the set of integers. And of course, the integers, the multiplication is commutative and associative, so we can take this expression here, K times NL, and we can rewrite that as N times KL, and that is certainly inside N times Z, since K times L is inside Z, because K and L are inside Z. And I also want to make the note that we already know that N times Z is a subring of Z, and hence that means N times Z is an ideal of the ring of integers. Our next example is going to be a little bit more theoretical. We're going to let phi be a ring homomorphism from ring R to ring S. So we don't know what rings R and S are. We don't know anything about them. R and S may be commutative. They may be non-commutative. But we have this ring homomorphism from R to S. Then it turns out that the kernel of phi is an ideal of ring R. And the thing that I want to start off with here is we already know from a previous video that the kernel of our ring homomorphism is a subring of R. And so all we need to do is we need to show that if R belongs to R, and let's call it K belongs to the kernel, then we need to show that RK and KR both belong to the kernel. And the way we do that is by remembering how we get into the kernel and what the properties of a ring homomorphism are. So let me make the following list of known facts. We already know that the kernel of phi is defined to be everybody inside ring R such that phi sends R to the 0 in the target ring. We already know that the kernel is a subring of the domain ring for our ring homomorphism. We also know that phi is a ring homomorphism, and that means that phi preserves both ring operations. So phi of A plus B is phi of A plus phi of B, and phi of A times B is equal to phi of A times phi of B. So what I want to do now is I want to look at the following thing. We're going to let R be any element of ring R, and K be a particular element of the kernel. So what that says is that we do know that phi of K is equal to the 0 element inside S. So phi of RK is going to be phi of R times phi of K, because phi is a ring homomorphism, and that's going to be phi of R times 0, because phi of K is equal to 0, and 0 times anything inside of a ring is equal to the 0 element. And that says RK belongs to the kernel of phi. Now, I would encourage you to stop the video and show that the other thing that we need to show, in other words, that we also need to show that KR is inside the kernel of phi. And I would encourage you to stop the video and do that on your own, because it's done in exactly the same way. So hopefully you did that. So we need to show this fact. But here again, phi of KR is phi of K times phi of R, and that's just going to be 0 in S times phi of R, and that's going to be the 0 in S, and therefore KR is also inside the kernel of phi. And when we put the facts together, that R times K is inside the kernel of phi, and K times R is inside the kernel of phi, that will imply that the kernel of phi is indeed an ideal of our ring R.